So a couple of weeks ago, I talked about how reaction videos were going to be the thing or was the thing that started to make me feel like a old middle-aged fart. I found something new over the last couple of weeks. Star Wars digital trading cards. Don't judge me, all right? So a couple of podcasts I listened to, they were sponsored by them. I'm not, obviously. Would be funny though if right as I said Star Wars digital trading cards, you know, it passed that little yellow line at the bottom of the thing and boop, Star Wars. Yeah, I'll give them a try because I liked having that stuff. Little Mark in the 80s liked collecting Star Wars cards. And now I'm not opposed to fake things. I got an obscene amount of fake trophies in my PlayStation account for a man my age. An obscene amount. And I even have real fake medals for all the races that I've done. This didn't see my finger. So yeah, I'd give it a try. Sure, why not? And it's like they're JPEGs, man. That's I mean, like this card here, the one with the Yoda standing on the, like, I think I've got that one like in a crate somewhere back at my mom's. I should dig that out. And what am I not getting? And I figured that if I treated it like a game, then instead of an actual hobby, like, oh yeah, I gotta collect them all. It made a little more sense, but albeit a game with really obscene microtransactions. So yeah, I'm gonna give you $100 of real money for this fake money. I don't want to do that. Right? And it's got the Tapjoy thing where, oh, watch this and we'll give you free credits. So we won't. This won't last much longer, I don't think. Although it did teach me a few things. For example, I learned that there was a guy in the Star Wars universe in the very first one, episode 4. One of the X-Wing pilots was named John Brannon, or John D. Brannon. You got to say the whole thing like a pimp named Slickback. But it's like John Brannon. It's like when it came to his turn, George Lucas just ran out of ideas, and I picture like he accidentally asked him what his name was, like, and the guy thought he meant his real name, but George was trying to come up with a character name. It's like, and your name is John D. Brannon. Sure, why not? Get in the stupid ship. All right, roll call. We're just about to invade the Death Star. So let's see. Wedge Antilles here. Jack Porkins, well, smooth. Yeah, of course it is. Dax Ralter here. John Brannon. Yeah. John D. Brannon, sir. Oh, whatever. Maybe that's like in the Star Wars universe. Maybe John Brannon is like a really ethnic name, you know, in a world of Dax, Biggs, and Plo Koon, and who can forget Kit Fisto. Maybe John Brannon is like the equivalent of, you know, Shamize or Shaniqua or Orangelo. You know, like, man, what kind of guy would name his kid John Brannon? Anyway, Biggs, dark lighter here. And I know there's a guy named Luke, but his last name was Skywalker. Is Luke Wilson really wouldn't have the same, you know. The force is strong in the Wilson clan. Just wouldn't have the same zing, you know, if his name had been Luke Brannon. Am I talking too much about Star Wars? Is that annoying you? Well, if you're watching this in the fall of 2014 when it's being recorded, if you don't like to hear a guy on the internet talking about Star Wars, you are in the wrong place and time now, aren't you? But we'll just keep going anyway. All right. All right. So for you General 1 folks who skipped ahead and just hit the little timestamp in the description, really good move today, I promise. But anyway, the General 1 folks, what we're going to do for you guys is we're going to talk a little bit about stoichiometry a little more before we finally say goodbye to it and get into some more stuff as we sort of slowly drift toward the end of the semester. General 2, guys, we're going to do one more ice table just to bring up a couple of more points that I don't think I've brought up before in any of the other videos that I've done. So general 1, guys, there's a couple more places where you finally, as you're finally near the end of reactions and you go into electrons and whatnot, assuming you're doing the traditional thing and that's some atoms first kind of thing that some instructors do. If you're with me, I do it the old-fashioned way, and we're about done with reactions. So there's a couple more places that you're going to run into stoichiometry. For example, let's take this reaction between sodium sulfide and hydrochloric acid to give you sodium chloride and hydrogen sulfide. Might have been one of the gas forming reactions you had to learn in the gas chapter. But let's say you react 50 grams of sodium sulfide and the hydrogen sulfide is collected in a 2-liter flask at 295 Kelvin. How much pressure would that gas exert? So, like I said in previous shows, you see talk of pressure and they're talking about a gas, and all that screams ideal gas law. So when in doubt, start with the ideal gas law and see where that takes you. So if you compare what's given to what's in the ideal gas law, we've got the volume and the temperature and the gas constant. But if we're going to calculate the pressure, we are missing moles of gas. But also recognize that this is a setup for a stoichiometry problem, even if I didn't just tell you that it was one a couple minutes ago and in the title card. It's got the same setup of every stoichiometry problem you run into probably. All right. Convert this much of this stuff to this much of this other stuff. So that's, again, it's always the same setup for any stoichiometry problem. Convert this much of to this much of. And the first step of any stoichiometry problem is to take what's given and convert it to moles. Excuse me. So since we have grams, we're going to use molar mass to convert to moles. Now we do our mole to mole conversion like we normally do. Once you're in moles, you just look at the chemical equation, and for every 1 mole of product or hydrogen sulfide, you have a mole of, it takes a mole of sodium sulfide. I think did I say hydrogen sulfide at the beginning? All right, we'll say I did. All right, so now you're in moles of hydrogen sulfide. So if we stop at this point, it turns out that we're going to produce 0.641 moles of that gas. So you go back to the ideal gas law. Now we know how many moles we have, or how many moles we're producing. So now we have everything we need to find pressure. So at this point, you just plug everything into the ideal gas law. Again, make sure the units match the gas constant, but they all do in this case. And you just solve for the thing you're looking for. So that combines a couple of things. It combines, some gas law stuff. But again, it's the same setup. You know you're going to have to use the gas law somehow because you see pressure and they're talking about a gas. But again, also notice that there's the telltale signs that it's stoichiometry. Convert this much of this stuff to this much of this other stuff. So it's just taking a couple of things that you've talked about in the past few weeks and kind of combined them into one problem. But still, you approach them the same way. Use stoichiometry the way you've used it before. Use the gas law the way you've used it before. Now you're just using them together. Right. So another type of stoichiometry problem you're going to run into toward this part of the semester is one that involves a thermochemical equation. And the thermochemical equation, sometimes students get confused about what that is. All that is the chemical equation with enthalpy change tacked on beside it. So again, this is chemical, thermochemical. That's all it is. One little note before anybody calls me out on it, I'm not entirely sure that's the enthalpy change for this reaction because if you've already looked into Hess's law and enthalpies of formation, which you probably will at the end of this chapter, I didn't have the enthalpy of formation of sodium sulfide, so I just guesstimated. I actually tried for a few minutes and I realized it really didn't matter for this problem, so just make up a number. All right. So, yeah, with a thermochemical equation, you might get a problem like this. Right, let's say that when those 50 grams of sodium sulfide reacts, how much heat are you going to release? So, again, it's the same setup as before, and as any other stoichiometry problem you've talked about in class or in these videos, this show, you know, convert this much of this stuff to this much of this other stuff. So again, just like before, the first step is to take what's given and convert it to moles. The next step is usually that mole to mole step. But in this case, instead of converting to another chemical, we're converting to heat. But we still look at our balanced equation, only this time it's a thermochemical equation, to get that our next conversion factor. According to our thermochemical equation, for every 1 mole of compound, we're going to produce 245.5 kilojoules of heat. So at this point, we're in the unit we want, and we calculate that it should be 157 kilojoules that are released. And some people might notice that, you know, there's the negative here, but I didn't include the negative in the problem. That's more of a technical thing, technicality, nitpicky thing, because the negative in the equation, the thermochemical equation, that's a relative thing. The negative just means heat's being released. But if you want to be, you know, split hairs, the question asked how much heat's being released. So if you technically keep the negative there and you get negative 157, you're kind of saying you're releasing negative heat, which doesn't quite work. It's like saying, you know, you gained negative pounds. No, you lost a positive number of pounds. But it kind of depends on who's asking the question and whether it's what type of environment, what type of test or quiz. You know, are you doing it on a website or are you doing it on paper? It may not matter. The sign may or may not be important. I don't know. Depends on who's asking you the question. For me, it usually doesn't matter. Or I try to rig the question where it doesn't matter, because don't let a sign confuse you about something that's not important at the time. You got other things to worry about, right? So, yeah, those are the last couple of stoichiometry little things you're going to run into. And later on, you'll see that after the thermo chapter, we talk about some other stuff, but I'll talk about that next time probably. For now, we'll move on to the general 2, folks. Hey, how you doing? So for you guys, I figured we'd do one more ice problem that talks about a couple of things that I haven't talked about. And I don't think this particular series of videos, or I don't even think I did it in the last batch of videos I did way back when over at my other channel, the Gen Chem Concepts channel. If you see the little link, probably here somewhere, if I remember to put it. Otherwise, I'm just pointing at a corner of a wall. We'll do one more example of an ice table just to bring up a couple of things that I think you should think about. But I should also add, if you're not really comfortable at all with ice tables, I would say watch last week's show and do some more work, and then see this one to see like a step up kind of problem. But it does involve stuff you might run into. So watch it eventually, or you're watching it now, but you know what I mean. All right, so let's look at this reaction where nitrogen dioxide is converted to dinitrogen tetroxide. And just to be a little different, I figured we'd do a KP, with respect to pressure, just to show you that whether it's KP or pressures or concentrations, it's still the same setup and same procedure. So yeah, don't let the fact that it's pressures throw you. That trips a lot of people. But again, it's just same ice table stuff as before. So let's see what the pressures would be at equilibrium if we started with 1.6 atmospheres of NO2 and 0.73 atmospheres of product. So as far as sort of recognizing an ice table problem, we're looking for pressures at equilibrium, E. We're given initial pressures, I. That's two of our three things in ice. So yeah, kind of like I was telling the stoichiometry guys before, you kind of see the same setups, where it just becomes same stuff, different equation. So, oh yeah, these initial concentrations, found the ones at equilibrium, yeah, ice table. So we start with an ice table. And so again, rho I is our initial pressures. And rho C is the change. And the last couple of examples I did, like last week's show and whenever, one side had nothing on it, or at least there was one reactant or product that was initially 0. So you knew you had to shift in that direction. But in this case, there's a little bit of everybody present. So you just can't look and say, oh, it's going to go this way or that way. You shouldn't pick the smallest amount because, stoichiometry may screw that up. And plus, the actual equilibrium, it may not go to the smaller side or the bigger side. The point is, you just can't look at it and tell. So in cases like this, before we can complete rho C, we got to figure out which way it's going to shift. So we have to calculate Q, our reaction quotient. So again, reaction quotients are just like equilibrium constants as far as setting them up. It's just for a reaction quotient, these pressures or concentrations, if you're dealing with QC, there are any other pressures or concentrations that aren't equilibrium. All right, so we plug these values into our expression of Q, and we get a Q of 2.56. And if we compare our Q to our K, we see that Q is smaller than K. So when Q is smaller than K, it's going to have to shift to the right. So we're going to lose so much of a reactant and gain so much product. And remember, the way you figure out how much you're losing and how much you're gaining, just make it all relative to the coefficients. All right, we're going to lose 2x worth of reactant, gain X amount of product, because there's a 2 there and a 1 there, or a 1's implied. So at equilibrium, we're going to have our initial 1.6 minus the 2x we lost in the shift, and our product's going to be 0.37 plus the amount we gained during the shift. All right. So now we can take rho E and plug it into our expression for K, which again is just like Q, except now we're talking about equilibrium pressures. So we plug in as much as we know up to this point, which is rho E for our top and bottom part of our ratio, and we know the K that was given. So now we solve for X. And last time we talked about solving for approximation, and at this point we can look at our setup and try to figure out whether or not approximation is okay. In this case, it probably isn't, because one way to kind of gauge whether or not approximation is going to work, remember, is to compare the value of K to the value of your initial amounts. And if they're really close to each other, it's probably not going to work. So in this case, I mean, they're both basically on the same power of 10, 10 to the 1 or 10 to the negative 1. They're within a factor of 10 of each other. So when they're that close together, approximation probably isn't going to work. Now, if you wanted to just try it, and you want to say, well, maybe we could approximate the bottom part to just 1.6. You do that, you solve for X, you're going to get X equals 21.9. And right away, you're going to see a problem there, because if you try to plug that into rho E, that gives you a negative concentration for your reactant. And that can't happen. And some people might notice you got an x at the top and you think, well, maybe you can approximate the top to 0.73. Well, if it didn't work at the bottom, it probably isn't going to work at the top. And also, too, you notice you really haven't saved you any work because you still got to do the whole FOIL method and figure out a quadratic like you would have anyway. And you still got to, you know, plug your A, B, and C into your quadratic formula to get two possible values. And let's say you've gone this far, so let's see what happens. All right, you put of these two, 0.9 is going to give you a negative concentration, I think, for the reactant again. The only one of the two, the only one that will remotely work is the 0.659. So you plug those into row E, you're going to get 0.28 for your reactant, 1.389 for your product. You plug those into your KP, you're going to get a K of 18, which is a little too high, or than what was given. So it's probably too much error for that to work. And somebody might think, well, maybe you can approximate both. Well, if you do that, then you're just there, your X goes away completely and you get 8 equal 0.2, and that doesn't make any sense. So you're gonna have to approximate, or not, you can't approximate, sorry, you're just gonna have to do the quadratic thing, which sometimes it happens. But remember, you could, for that particular problem, you know, once you do enough examples, more practice problems, you kind of see that, yeah, when the K and the initial concentrations are that close together, it's not even worth trying. Although the first time we tried it, where we made the bottom part approximated, you notice we didn't lose that much time by trying. The other two things, you know, would have been way too much work. Especially that last one, can't take X away completely. But like I said last time, if you're really not sure, then give it a try, because usually you don't, if it fails, you didn't lose that much time compared to how much you would have saved if it had succeeded. But yeah, when they're that close together, it's probably not going to work. The bigger apart they are, they're more certain you can be about whether or not it works. But we talked about that last week. So finishing this problem up, yeah, forget that. So it looks like we're gonna have to work it all out and come up with a quadratic, which would be this. If you compare this in the last scenario, you'll notice only the middle part changed. But you plug that into your quadratic equation, and you get an X of 1.02, or it can be 0.607. Of these two, again, the first one's not going to work because I believe it's going to give you a negative concentration for NO2. So it looks like 0.607 is our value for X. So you plug those two into row E. You get 0.39 for your reactant, 1.337, hey, elite, for your product. And now when you do your check and you plug those into your, back into your expression of K, you get something that looks a lot better. It's pretty much dead on with a couple of sig figs. So again, that's a couple of things to watch out for when you start to get more into the ice table stuff. One, not every instant is going to be one where you have a zero and you can clearly tell which way the shift's going to happen. But remember, the way you figure out shifts quantitatively, i.e. with math, is you calculate the Q. So once you compare your Q to your K, then you can see which way the shift's going to occur. And in that case, once you know that, your ice table setup's just like any of the others that you've run into before. And like I said, as far as when it's okay to approximate, as you get better at kind of, or you do a little bit more practice, you kind of get an idea of when it's clearly not going to work and when it really probably will. Like you compare this to the examples in the last show I did. Yeah, last week we had one where the K and the initial concentrations, they were different by a factor of 1 billion. So when they're that different, approximation is probably going to work. It's definitely going to meet the 5% rule. When they're that close, like 8 and 1, yeah, they're too close. You're probably wasting your time trying. But there's that gray area where it's, around 10, if they differ by a factor of 10 to the negative 4, I don't know that's not working anymore. 10 to the negative 4, negative 5, negative 6, especially like negative 4-ish region. When they're that close, it might work, might not work. But in those cases, again, it's not going to kill you to try it. And if it works, you've saved a lot of time because you don't have to do any of that FOIL or quadratic stuff. And if it doesn't work, you didn't lose that much time trying. All right. So next time, I'm not going to talk about stoichiometry or ice tables. I'll probably talk about some electron stuff for the General 1 folks. And I don't know, General 2, what are you guys doing next? See, you guys are doing thermo, I think. No, acid-base stuff. So maybe some pH acid-base stuff then. We shall see. So